Let's do the same thing for the propagator of the quarks. Take the propagator of the full theory, expand in this limit. So first of all, propagators always involve p squared plus I0. In our decomposition, that's n bar dot p, n dot p plus Minkowski p perp squared plus I0. And if you look at the size of these things, they're all the same size. This guy is lambda 0, and this guy is lambda squared. And this guy is just lambda squared by itself. So the two guys are the same size, as though they become the same size for different regions. This is lambda 1 squared, if you like. So I don't drop anything in that propagator. We'll see that actually that's not entirely true, and it does depend on what type of things you're interacting with. But if I just have p's that are collinear, as I've drawn here, then there's nothing to drop. So if you look at fermions that are collinear, and you look at IP slash over p squared plus I0, you can decompose p slash out in terms of n slash and n bar slash, write it out in terms of the coordinates we're using. And then in the numerator, there is you keep the full denominator, but in the numerator, there is one momentum component that's larger than the others. And that is the n bar dot p piece, which is order 1. So there is a simplification of the p slash, and it's related in some ways to the simplification of the spinners. If you take two of these guys and you do the sum over spin, you'll actually get n slash over 2 n bar dot p. Yeah, so the right way of thinking about the numerator here is that if you do the sum over spins of sort of two of these spinners, like this, that's giving you the numerator. And if you look at sort of the overlap of this, if you look at any amplitude, you also have to take into account what I haven't written yet, which is this. And that's going to go like n bar slash. OK, so what happens is you have n slash and bar slash, and that gives you the projector, which then overlaps order 1 with the spinner. Yeah, well, that's a good question. Later. But that's a good point. OK, so we can ask about if we have some propagator for a fermion, then what does it look like? And you can take that first order term, and we can write it in a way that kind of is reminiscent of something more like NRQCD or this nucleon theory or even HQET. It's just another way of writing the same formula that is sometimes useful. We just divide through by the n bar dot p. And then it's n dot p plus p perp squared over n bar dot p. And then there's the I0, but the sign of the I0 will depend on the sign of the n bar dot p. And that's actually the fact that this could be both plus I0 or minus I0 is the same thing as saying that there's antiparticles and particles in the theory. If it was just plus I0, as it was in HQET, we only had the particles. Here it could be either sign. We have both. And so this thing, again, has both particles and antiparticles, which we saw when we were doing the spinners as well. And if we wanted to think about particles and antiparticles separately, then we could have a definite sign for the I zeros. But if we want to think about them in a combined propagator, then we have to write it this way. All right. So once we know what the propagator is, then we can also figure out what the power counting of the fields are, because the propagator tells us what the kinetic term should look like of the Lagrangian. So let me show you how that works. Okay, so where does the propagator come from? The propagator comes from the time order product of two fields. And in this case, it comes from the time order product of a field for this Cn component that we were talking about. And if we just take the free kinetic term, which is the Lagrangian that would give that propagator, that's enough to determine the power counting for fields, as is always the case in any effective field theory. So we haven't figured out what the Lagrangian is, but we know something about what it's going to look like. So let me write down enough of that to determine for you what the power counting would look like. So when I write it this way, as I wrote it, where it's linear in this n dot p derivative, you know that what that's going to correspond to in the Lagrangian is some n dot partial. And I have to have an n bar slash here, because that always comes along with an n, decomposing the metric. If you ask about the power counting here, well, d4x has all four components of k, and x is the inverse of k. So the way that you assign a power counting for x is that you say the phase should be of order 1. So the scaling for x is the opposite of k. So that fixes that d4x should be lambda to the minus 4. Okay, so x plus times k minus is of order 1, etc. And that tells you how many powers to associate with the d4x. We know how many powers to associate with this partial, because that was our momentum. That's lambda squared. And actually, the other terms here will also be lambda squared. And then we just say, well, let's let the power counting in this field be arbitrary, lambda to the a. And so if we do that, then we get an overall scaling for this Lagrangian that's lambda to the 2a minus 2. Okay, 2 to the powers of lambda minus 4 are canceled by the partial, end up partial, and we get that. Now, the way that we do effective field theory is we look at the lowest order term, and we count everything relative to that. So what we do is we say we want the lowest order Lagrangian to scale like lambda to the 0. And you can think of that roughly in the power counting sense as normalizing the free kinetic term, or normalizing the kinetic term in general. And then that, once you do that, then you're fixed what the scaling of the field is. Cn's of order lambda. And that's different than the mass dimension. So I said that we were going to be doing a power counting that's different than the mass dimension. If we looked at the mass dimension of this field, Cn would have mass dimension that's 3/2, whereas it has, if you like, a lambda power counting dimension, which is 1. So if I look for the powers of lambda, that's 1. Okay, and that was one of the things I told you was going to happen, is that in this effective theory, we wouldn't just be counting mass dimension, we'd be counting something else. Okay, so that's collinear quarks. We can do a similar thing for collinear gluons. We may not get to the end of that discussion today, but let's start it. the momenta for a collinear gluon scales the same as the momenta for a collinear quark. What means collinear doesn't distinguish between quarks and gluons. So p squared, the full p squared, is still something that we're going to leave together. And let's just consider looking at the propagator in a general covariant gauge. And asking kind of the same type of thing that we did over here about the scaling of the field. So the propagator for two collinear gluons in the general covariant gauge, time ordered product, vacuum matrix element of two fields. Ignore the A's, ignore the subscript n's right now. I'm just writing down a full theory result. We called C something else, so we better not make that the gauge parameter. So let me call the gauge parameter tau. So that's the gauge parameter of the general covariant gauge, and this is a full theory result. When the thing that makes it collinear is if we say that k has a collinear scaling. So as above, k squared is k plus k minus plus k perp squared. That's of order lambda squared. And there's no expansion in there. And there's two k squareds here. There's one there and there's one there. And if you start looking at g mu nu minus k mu k nu over k squared, you also find that the terms there are the same size. So there's actually, let's see how that works. So let's do an example of that. So g perp mu nu was just 1. So that's obviously something that has no scaling. And if you compare that to k perp mu, k perp nu over k squared, k perps scale like lambda, k squared scales like lambda squared. So this is lambda squared over lambda squared, so that's also lambda to the 0. So both the g perp mu nu and the k perp nu term are the same size. Yep.
If it happened that didn't work out, could you choose the gauge parameter to have a scaling with lambda?
You could, but then you'd be restricted to the classic gauges that you would be able to use in the effective theory, and then you'd have to ask what gauge invariance would mean. So if I don't make any restrictions on tau, I don't assign a power counting to it, that means that I should have, my effective theory should allow all these gauges. And I actually want that. That's a good question. You can do the same thing looking at, for example, g plus g minus. That's also 1, so lambda 0. Then you get k plus k minus over k squared. That's also lambda squared over lambda squared. So this is what I was saying, that the two terms are the same size. If you dot in n mu, n nu, that kills the g mu nu. G plus plus is 0. And then you just get k plus squared over k squared, which is lambda to the 4th over lambda squared, which is lambda squared. So when the g mu nu is not 1, then the k mu k nu term can still determine how big something is, and that's what would happen for these off-diagonal terms. So if we go through the same type of exercise that we did for the fermion, d4x scales like 1 over k to the 4th. So that's lambda to the minus 4, just as before. And actually, if we were to do the following, if we were to write this as, I should have done it up there. If we were to write it as minus I over k to the 4th, k squared g mu nu minus tau k mu k nu, the k to the 4th just matches up with the d4x. So those take care of each other. And then the fields here have to match up with the rest. So the scaling of this should be the scaling of the a mu, a nu. And that basically means that a mu and a nu scale like a momenta. So A mu n for this collinear gluon scales like K mu, scales like lambda squared 1 lambda. Let me write that one more time. And that's also a nice thing because it also means you can form a covariant derivative that's homogeneous by combining together K mu, if I write it this way, K mu and GA mu, I can get a covariant derivative where for each component of K, I also have a component of the gauge field that's the same size. So you could have argued it originally just from gauge invariance that you want to sort of have fields that are of the same size as your momenta. But we did it a little bit differently here. So it's nice that that comes out. It all hangs together. So next time we'll talk about the fact that what does it mean that the gauge field has components that are scaling in a different way. In particular, there's a component of the gauge field that's order 1. There's no power suppression relative for that component, and we'll talk about what implications that has.
So
Yeah.
So what about in a non-covariant gauge, like n bar at a equals 0?
Yeah, so you could go through this argument in that gauge as well, and it will work.
But you'd have n bar at a equals 0, so.
Yeah, that's fine. That's just a restriction on the. You can still assign a scaling to it, and then there's a special choice of it is 0. Scaling and values of things are not the same thing, right? Like you could have a field that scales like 1 in the power counting, but it happens to be 0. And that's OK. Yeah.
I have a question about SET1 and SET2.
Sure.
So in the example of having one jet
Yeah.
and having one hadron, like the pion,
Yeah.
why do I need to have different degrees of freedom to describe these two things?
Yeah, it's really because of the way the modes sat on those hyperbolas, that in the case of the hadrons, you had the soft modes and collinear modes on the same hyperbola. And that's going to change how the effective theory looks.
Yeah, but I mean, from a physical point of view, why the hadrons, the constituents of the hadrons behaves in a different way than the
Yeah,
jets?
so one way of thinking about it is if you just had the collinear modes alone and you didn't have the soft modes, then it would be very similar. It would just be that the hyperbola moved down. Okay, and you could think maybe those two theories are the same. And there's examples of that, actually. There's one example that we'll cover where you don't need soft modes. And then you can't really tell whether you're using SCT1 or SCT2. But if you have a process that has both soft and collinear modes, then it's the way those modes talk to each other that distinguishes between SCT1 and SCT2.